function. Composite is something that we're going to compose. We're going to kind of not make it up, but put it together. Okay, so when you have two functions, f of x and g of x, we can create something called a composite function. Actually, we could create several composite functions from these two functions, but a composite function would look something like this. So the notation is, we're going to create this new function called h of x, and we write it this way. Okay, and this is not the word fog.
Please come to guidance. Eliza, please come to guidance.
You would read this out loud as f of g of x. Okay, and this is one form of notation that's quite commonly used, but what it means is this, f of g of x. Okay, and essentially what we're going to be doing is, to create this composite function, is replacing the variable x in f of x with the new function, g of x, some other function. So instead of like subbing in a number to f of x, f of 2 equals whatever, we're going to sub in another function. Okay, so it'll be some other sort of expression that has an x in it. Okay. This is often how a composite function will be given to you. You might be asked to write what is the equation for f of g of x, and it'll be this notation. This is supposed to be like a, I don't know if you guys can notice this, this is supposed to be like a tiny o. It's supposed to be smaller. Like if you look at it typed, the font is smaller than the other two letters. But I personally always rewrite these this way, so that I know which function I'm putting into which, right? I'm replacing the x's in f of x with this new function g of x, okay? Now you can also do it the other way around. We could also create some other function, you know, let's say k of x, which is g of f, whoops, just an O, of f of x. And in this case, we're going to replace the x in g of x with the other function f of x. Okay? So one of these functions is sort of treated like an outer function, and one of them is the inner function. The inner function is what you replace the x's with. Okay? When we are writing these things, essentially what we're going to do is replace the variables in the outer function with the inner function. Okay, and what I'm hoping is that this will make the most amount of sense when we look at some examples of doing this. So, for example, suppose we have these two functions. One of them is f of x equals 2x plus 1, and the other one is g of x equals 3x. And we're going to kind of do this both ways. So the first thing that we're going to do is find f of g of x. Okay? Now when I'm approaching these questions, although it's written this way, I always rewrite it as this is the outer, this is the inner. So f, instead of f of x, f of g of x. Okay? And then what I like to do is write out the outer function. So the outer function is 2x plus 1. But I'm not going to write an x in there. I'm going to replace the x with a set of brackets. So this is equal to 2 times x, so 2 times a set of brackets, plus 1. And what I'm going to put in there, what do you think I'm going to put in there? G of x, right? So that goes in there. Okay. If you want, you can break this down a little bit more. So, especially when you're working with, an outer function or an inner function that involves a few more terms or things like that, you could also write it this way. Instead of the g of x part, put the 3x in there. Instead of taking f of x, we're looking at f of 3x. So we replace the x's in the original function, f of x, with 3x. Okay? Either way, you end up with the same function. And then at this point, you would simplify it. So we can simplify this to be 6x plus 1. Okay? Now, if we do the same sort of thing, but switch the function, so now g of x is the outer function, f of x is the inner function, this is g of f of x. Okay. Then I think actually I'm going to do it this way first. I'm going to say, okay, well, we're taking g of another function. That other function is 2x plus 1. F of x is 2x plus 1. So I'm going to write the function for g of x, which is 3x. But I'm going to replace the x with a set of brackets. So it's 3. The function is essentially 3 times something. So ordinarily, we would put in a number, right? Like what's g of 2? It would be 3 times 2. What's g of negative 10? It's 3 times negative 10. Here we're taking g of 2x plus 1. So it's 3 times 2x plus 1. Okay? And then we would evaluate this as well. And this one, when we expand, or not evaluate, I suppose, but, sorry, that's 6x. Expand. Okay, so this is 6x plus 3. Okay? Does f of g of x equal g of f of x? In this case, no, and almost always it will be no. Very occasionally, you will see a function where there is this property where it doesn't sort of matter what order you go in, but that's not typical. Okay? So the answer to this is no. You got to pay attention to what letter comes first in this notation, because the first letter is the outer function. Great. So let's try some other ones. Here we have f of x equals x squared minus 4, and g of x equals x plus 1. So first we're going to start by figuring out f of g of x. Okay. So the first thing I'm going to do is I'm going to replace the g of x with the actual definition of that function, which is x plus 1. So what I'm taking here is f of x plus 1, because g of x is equal to x plus 1. And now what I'm going to do is I'm going to rewrite f of x, but replace the x with a set of brackets. So it's x squared minus 4. It's going to be bracket squared minus 4. And in those brackets, I'm going to put whatever is inside here, the x plus 1 in this case. Okay. Now I have to evaluate this, or sorry, I keep saying evaluate. I'm not evaluating it, I'm simplifying it, right? Because at the end of the day, this one is going to work out to be quadratic. So we would probably simplify this. So if I expand x plus 1 squared I'm going to get x squared plus x is plus 2x plus 1 minus 4. And so that works out to be x squared plus 2x minus 3. Okay? You can also create a composite function with just one function. So I could look at f of x or g of x, that sort of thing as well. And essentially what I'm going to do here is just replace the function itself in for x. So same sort of idea, f of, okay, what's this? I'm just going to like copy and paste essentially, right? So it's x squared minus 4. Okay, so that's the first thing I'm going to do. Now I'm going to rewrite this function, x squared minus 4, but replace the x with brackets. So the overall structure of the function is we're taking something and squaring it, then subtracting 4. And now I'm going to put whatever's in here in here. Okay. Now, some people can go from here to here all in one step without having to write this middle piece out first. That's fine. You can do that as long as you don't make mistakes. Okay. And then again, yeah, we would sort of want to expand this and simplify, collect like terms. So x squared minus 4 squared. Let's see, that's x to the 4 minus 4x squared minus 4x squared minus 8x squared. And then plus 16 minus 4. So x to the 4 minus 8x squared plus 12. Okay? All right, now we can also do a composite function with 3 functions. This is f of g of h of x. So now there's like an innermost function and then sort of a middle function and outer function. Now this one I would do in a couple of steps. So the first thing I would do is rewrite this in the other notation, because for me that really helps to see what's the innermost thing and what's the outermost thing. So the outermost thing is f of g of h of x. Okay. Now with these types of questions, what I personally do is I work this out off to the side, right? What's just that piece? So if I'm looking at g of h of x, well, h of x is 2x. So I would be looking at g of 2x. Okay. And that is, let's see, g of x is x squared minus 2. So it's something squared minus 2. And the something has to be this 2x. Okay? And now I'm going to simplify that. So let's see, 2x squared is 4x squared minus 2. Okay? Now I can take this piece. That's g of h of x. So I can replace this whole thing with 4x squared minus 2. This is f of 4x squared minus 2. Okay, and now I can look at, okay, well, what's f of x? It's negative 3x plus 5. So I'm going to rewrite that function, but again, replace the x with brackets. Negative 3 times something plus 5. And in here, I'm going to put whatever was in here. 4x squared minus 2. Okay, and then, at this point, simplify. So what is that? Negative 12x squared, and then plus 6 plus 5. So negative 12x squared plus 11. for fun. Will you see any crazy iterations of these? Okay. Well, the point in a context, it's not going to be easy at this point for me to give you examples that are really genuine, where I can make a clear connection to the world. What I can say is that, let's say you take something like, we're going to look at this in a minute, okay? But let's say you take something like this. Y equals 2x plus 7 to the 11. Something like that. Okay? Now, this is a polynomial function. It's degree 11. We could expand that out, multiply that binomial by itself 11 times to get the full expansion. Okay, that's one option. But in terms of what we might want to do that with that function and what we might want to do with it is going forward, look at things like what is the rate of change of this function? So what is the steepness of the curve of the function at any given point, right? If there's a curve, we can't talk about the slope. You think about the slope of a line. You can't really think about the slope of a curve, but you can draw something called a tangent line, which is a line that touches the curve at any given point. And that is the instantaneous rate of change, right? Think about like rise over run, that sort of thing, of this curve. Okay? So what we might want to do with a function like this is analyze things like what is the instantaneous rate of change? How sort of steep, shall we say, is this particular curve at any given moment? We might want to think about that. We also might want to analyze it with respect to things like local max and mins, right? I talked about polynomial functions. They can have these sort of humps and valleys and things like that. So we might want to analyze that sort of thing. We also might want to analyze things like, I spoke about the word concavity, which is, think of a parabola. Something that opens up is concave up. Something that opens down is concave down. Okay? Now, when we are doing that analysis, having the function in this form rather than expanded helps us to actually expedite or make that type of analysis much more efficient. This is actually written as a composite function. It is f of g of x, where f of x is x to the 11, and g of x is 2x plus 7. Okay? Now, what we actually do in that analysis is we can sort of learn rules to work with each of those functions at a time to be able to do that analysis. And so I suppose, when do we actually take two functions and mash them together to make a composite function? Not really that often. But what we do is take something that has the potential to be written as a composite function and write it that way so that it makes it easier to do the analysis on each piece at a time. Yeah, exactly. Okay, so that's like not a very satisfying answer, but that's sort of where it's leading to. Okay, right now though, yeah, we're learning the mechanics of it, and it is very hard at this point to see why. Right? It kind of seems like we're just doing it like, I don't know. Do you guys, okay, I gotta ask, because you guys ask me this stuff all the time, or students in general ask me this stuff all the time. Do any of you guys play sports? Okay, you do like the suicide sprints or whatever? Do you guys ask your coaches, why are we doing this? You're kind of learning, you're gaining the fitness. You're gaining the fitness to be able to go and play the sport better, right? That's kind of what we're doing here. Right now, honestly, it's an exercise. That's all I can say, right? Yeah. Okay, so let's keep going. So if f of x, given f of x equals x minus 3, and g of x equals the square root of x, determine the following and state any restrictions. Okay, so now we're going to have some restrictions because one of the functions that we're working with is a radical function. Okay, so the first thing we're going to look at is f of g of x. So this is f of, let's see, square root of x. And that is, let's see, I'm going to rewrite f of x, but replace the x with the brackets. With brackets. Oh, whoops, sorry, x. Okay. And at this point, you know, the brackets aren't really necessary, so you could write this if you want as just square root of x minus 3. Okay. What are the restrictions on that? On x? Yeah, so here, x must be greater than or equal to 0. And in fact, what this really is it's a vertical translation of the function y equals root x down 3 units. Okay? When we look at g of f of x, okay, now we're looking at g of x minus 3. Okay, now g of x is the square root of x. So this is the square root of something. And that something is the x minus 3. Okay? You don't need a bracket, no. I personally just get in the habit of doing it because if there was like a coefficient here or if this was squared or something like that, then yeah, that bracket would be really significant. Okay, but no, you don't. So what's the restrictions here? Yeah, x is greater than or equal to 3. Now this is essentially a horizontal translation, 3 units right. Okay? All right, so here's another one. And this question, honestly, really is just about understanding. If you ask me when do we ever do this sort of thing, where we essentially take a function, f of x, that's defined over 4 points, and another function, g of x, that's defined over 4 points, and then take f of g of x, like in the field, do we ever do this? No, right? This is just developing an understanding of the concept. Okay, so we're going to look at f of g of x first. And when we have this type of function that's discrete, right? It's not continuous, it's just 4 points. We actually have to sort of scrutinize the composite function over every single point. Okay, so the answer to f of g of x is also going to be discrete. We're looking at f of g of x. Okay. These points over here, each point is x, g of x. Okay. So in fact, this function, g of x, only has a domain of 3 values, 6, 2, and -1. Those are the only x values that we're allowed to put into g of x. Okay? Now, when we put a 6 into g of x, that's our x value, we get an output of 3. That's our g of x value. Okay? So when we're looking at f of g of x, we have to look at f of g of all of the domain values for which this function is defined. Now, this function is defined when x equals 6. It's defined when x equals 2. And it's defined when x equals -2. Okay? Those are the only x values that I'm allowed for g of x. Okay, now, f of g of 6, well, what is g of 6 equal to? When x is 6 rather, g of x is 3. Yeah, so this is actually f of 3. And this one, f of g of 2, when x is 2, g of 2 is -1. So this is f of -1. Whoops, I forgot a bracket there. F of g of -2, when x is -2, g of -2 is 1. So this is f of 1. Okay, now I can go and see, okay, well, do I have a value for this? Is f of 3 defined? Yep. This is, let's see, what is it? 5. F of negative 1 is 4. F of 1 is 6. So in fact, if I were to put this f of g of x into a set of points, well, the first one had an original x value of 6 and sort of an output value of 5. So the first point in this function would be the point 6, 5. Okay. The second point had an original x value of 2 and an output value of 4.
Okay, so that is 306 A and B. I'll continue.
Okay, and then finally, the last one has an x value of negative 2 and a y value of 6. So those are the 3 points that define this new composite function, f of g of x. Okay, now we're going to try and do it the other way. If we're looking at g of f of x, okay, well, g of f of x is only defined for 3 x values. 3, negative 1, and 1. So those are the only x values that we're allowed to put in here. So we're going to be looking at g of f of 3. We're going to be looking at g of f of negative 1. We're going to be looking at g of f of 1. Okay. G of f of 3. So f of 3 is what? 5. So this is g of 5. This guy is g of 4. And this one is g of 1. Okay. All right. Oh, sorry, this is 6. Yeah, you're right. F of 1 is 6. Yeah, f of 1 is 6. When x is 1, f of x is 6. There we go. Okay, so what's g of 5? Yeah. Doesn't exist. Yeah. Because this function g of x only has 3 x values in its domain, and 5 is not one of them. So this does not exist. Okay. G of 4. 4 is also not within the domain of g of x. So this also does not exist. The third point does exist, right? G of 6 is 3. But overall, as soon as one point doesn't work, the composite function does not exist. Okay, so overall, does not exist. Okay, and in general, when you are looking at a composite function, essentially, if you think about f of g of x is the range. Okay, you are inputting the range of one function into the domain of another. It'll only work if the entire range of that function is within the domain of the outer function. Okay, so these are only defined if the range of the inner function is with of the outer function. We're taking the y values of one function, inputting them, making them into x values of another. There has to be overlap there. All right, evaluating composite functions. So there's two ways to evaluate these composite functions, and now we're not going to be talking about this weird sort of situation where we have two discrete functions that have nothing to do with x. They're just a set of points. There's no equation involved. We're talking about how do we evaluate them when there is an equation involved. I can't talk today. Okay, so there's two ways to go about it, right? If you're looking at f of g of x, something like that, you can evaluate, and in this case, you're going to be given a number there. You can start by evaluating the g of that number. Let's say you're looking at f of g of 2. Figure out what g of 2 is. Let's say g of 2 is 5. I don't know. Then put a 5 in there. Okay? So you can evaluate, I can't write either today. Evaluate the inner function first, and then put that value into the outer function. Okay, you can do that. So, for example, let's say we're working with f of x equals x cubed minus 1 and g of x equals 2x plus 1. And we want to evaluate f of g of 2. So what I mean by this sentence over here is I could evaluate g of 2 first, right? So I could say, okay, what's g of 2 equal to? G of 2 is equal to 2 times 2 plus 1, which is what, 5? Oh, isn't that what I just said? Didn't I say if x is 2, y is 5? Okay. And then you take that 5 and put it into f of x, right? Now we're looking at f of 5, and that's 5 cubed minus 1. 125 minus 1 is 124. Okay, so you can do that. The other thing you could do is come up with an expression for the composite function in terms of x, and then just plug the original x value in, right? Or get an expression for f of g of x, then plug in the x value and evaluate. Okay, so what I mean by that is if we're doing this example here, let's actually figure out what's f of g of x. Okay, f of g of x is g of x was 2x plus 1, f of 2x plus 1. Okay, now that was something cubed minus 1. We're going to put this 2x plus 1 in there. Now you can, into this equation, you can directly input that 2, and you'll get the same value, right? So if we start with this and say, what's f of g of 2? It's 2 times 2 plus 1 minus 1. Sorry, cubed minus 1. And that's still 5 cubed minus 1 is 124. Okay, now, why would you maybe do it the second way instead of the first? Yeah, firstly, when it gets more complex, or the other thing is if I ask you to evaluate that function over several points, so you'd have to keep doing it over and over and over and over again. Sometimes it's easier to just get the equation in terms of x, so you can plug it right in there, okay? But yeah, like you can do it either way. Okay? If we were to evaluate this one, g of f of 2, Okay, well, again, we could start by looking at this first. F of 2 is 2 cubed minus 1. So that's what? 8 minus 1 is 7. So now we're going to look at g of 7, which is 2 times 7 plus 1. That's 15. Okay, or f of 2. Oh, we just figured out f of 2, right? We know what this is. This is 7. We just did it over there. This is now f of 7, which is 7 cubed minus 1, so 342, I think. Okay. All right, so now we're going to look at this graphically. Use the graph of f and g below to evaluate the compositions. So here I would for sure evaluate the inside first and then plug that output, you know, whatever. For example here, f of g of 6. What's g of 6? I don't know. G of 6 is 3. So we need to look at f of 3. F of 3 is 0. Okay. F of g of negative 2. So we want to look at g of negative 2. 7. So f of 7 is 2. Okay. G of f of 3. Okay. F of 3 is 0. So yeah, g of 0 is 6. G of f of 7. F of 7 is 2. So g of 2, 5. No? Is that right? Yeah, 5. And then f of 9. So f of 9 is 2.5. Is that right? No, that's 8. Huh. F of 9 is 3. Okay, so here we're looking for f of 3, which is 0. Okay? So far, so good? Okay, so this is kind of what I was getting at earlier when the question was asked as to, like, why do we do these? And the honest answer is that we don't often, in reality, sometimes we do, but not often, create a composite function. More frequently, we take a function that's already given to us and say, how could we break this up into a composite function? Okay, so now what we're going to do is sort of try and go the other way. So let's say we have this function h of x equals 5x minus 7. Okay, so you can think of this function being composed of two parts. One of them is that we take something and we multiply it by 5. The other one is we take something and we subtract 7. Okay, so the question sort of becomes, if we were to compose this function out of two others, how would we put that together? Is it the piece where, you know, we take another function, multiply it by 5? Or do we multiply the x value by 5, replace the x with 5x, and then subtract the 7? Okay, so what we're going to do here is just kind of see if we go in either order. And the question is, what's the outer function here and what's the inner function? Which way does it work out, right? If we're looking at h of x equals f of g of x, if this is f of x and this is g of x, then f of g of x would be f of x minus 7, and f of x is 5x, 5 times x minus 7. Okay, or 5x minus 35. If we do it the other way, g of f of x, this is g of f of x is 5x, and that's something minus 7, so then we put the 5x in there. It looks like it's the second way. Okay, and this example is kind of arbitrary because with a linear function, honestly, we would never pick it apart in this fashion. So it's, again, more of an exercise. But the point is that having this skill, being able to look at a function and say, if this were to be a composite function, what would the parts be? What would the inner function be and what would the outer function be? Okay, that skill is something that is very, very useful. And that's the skill that we actually, in reality, use the most often. Okay, so for example, suppose we have this function h of x equals x minus 6 to the power 4. What are the two functions, g of x and f of x, such that h of x equals f of g of x? Right? So if this had been composed of two other functions, what would the equation of the inner function be? And what would the equation of the outer function be? And what you kind of want to try and do is zoom out a little bit. Yeah. Yeah. Okay. So I'm not sure if you guys heard that, but the only thing that I would do personally is I tend to look for the inner part first. What am I inserting into something else? And it looks like I'm taking this expression x minus 6 and raising it to the power 4. So if that x minus 6 was my inner function, right? If g of x equals x minus 6, what am I doing to that? I'm taking that, raising it to the power of 4. That means my outer function has to be something to the power of 4. Okay? And honestly, this is where these things are most valuable. Okay? So let's practice this a little bit. What could, if h of x equals the square root of 3x minus 2? Now this function, by the way, is not something weird that's made up. Like this is a function that we saw in radical functions. It's a transformation of y equals the square root of x. Okay? What would the inner function be and what would the outer function be? Yeah? Yeah. Yeah. The inner piece is that 3x minus 2, right? And I think part of the challenge here
Cameron, can you please call the office? Ms. Cameron, call 2322. Thank you.
Is people get caught up with the jargon around g of f of x or f of g of x. Think inner and outer. What's the inner piece? What's the outer piece? Okay. What about this guy? H of x equals x minus 4 squared plus 3 times x minus 4 plus 4. Yes, Lachlan.
F of x would equal x squared plus 3x plus 4, and g squared would be g of x would be
Yep.
x minus 4.
Right. Okay. It's so interesting to me because a couple of people have now said the outer function first. I just don't see it that way. I always sort of look for that. I don't know. That's so interesting. I guess, I don't know. People see things in different ways. Yeah. Okay. So, yeah, you take this same binomial, you're squaring it. Then you multiply it by 3, then you add 4. So that inner piece, it's kind of the piece that you keep inserting in. Okay? Now this one may be a little tricky to see unless you do something else first. Yeah, factor it, right? Because this is actually x minus 3 times x minus 3. It's a perfect square trinomial. So when it's written this way, it's probably easier to see what the inner function is and what the outer function is. Yeah, x minus 3 is the inner function. And what about the outer one? X squared. Yeah. Okay. And one other thing that I'll add, by the way, is that when you're taking something like a linear function and inserting it particularly into a quadratic, right? Honestly, it's kind of like 6 of one and half a dozen of the other. It doesn't matter whether you think about it as a composite function or just as a quadratic function. But in terms of what we're going to do with this next, which actually, to be honest, is not going to be in this course. It'll be in another course, which is all of those things around analyzing things like what is the rate of change of this function at any given moment in time, right? How steep is that curve? What's the domain and range? What are the endpoints? What's the concavity? Things like that, okay? For something like this one, where you're taking a linear function and inserting it into a different type of function, into a radical function, being able to think of it in this way is very, very, very useful. Okay? Okay, so here's another one. Now we're kind of working backwards. Given h of x equals f of g of x, determine g of x. So now what we want to know is what's the inner function? Okay, we know h of x in this case equals square root of 9 minus x. So that's the composite function. F of x, which is the outer function, is the square root of x. What's the inner function? 9 minus x, yeah. Okay, what about here? H of x equals 12 over 7x minus 2 squared. And f of x equals 12 over x squared. Yes. Yeah, 7x minus 2. That's what we're replacing the x with. Okay? So here's one example of a context type situation or an application of these things. The cost of producing X engines, cost of producing a certain number of engines, X engines, is C of X equals 75X plus 900. Okay, so it looks to me like this cost function, there's some fixed cost in there, that's the $900, and then the engines are 75 bucks a piece. Okay, so there's the cost function. The number of engines produced in T hours is given by the function X of T equals 10.5T. Okay, so here's what's happening. The cost depends on the number of engines, but the number of engines depends on some other variable, and that depends on time. And so now what we want to do is determine what C of X of T is. What is this composite function C of X of T? And what I actually want to talk about first is this piece. What does this represent? Because essentially what we're doing here is taking a function that depends on a variable x, the number of engines manufactured, and relating it to a whole other variable, time. Okay? So what we're going to end up with is a function that connects the cost to the time. And the number of engines is kind of like the middleman. Okay? So this is actually going to represent the cost of producing reducing over time. Okay, it's like that x of t piece is like a holding place for a little while that, takes the output of one, inputs into the other so that we can now connect the one up to time. And the x of t is the middleman. Okay, so determine c of x of t. Let's do that. C of x of t is going to be c of, well, x of t is 10.5 t. And that is, now I have to look at the cost function. It's 75 times something plus 900. So 75 times something plus 900. But now I'm going to put this guy in there. So essentially, by creating this composite function, I've sort of changed the independent function, or the independent variable, rather, to be the number of engines to now time. So I don't know, what's 75 times 10.5? 700. Okay, so it looks to me like it costs $787.5 per hour to produce, plus this 900, which is some sort of fixed cost. Okay? All right, so determine the cost incurred after 8 hours of production. So at this point, now that we have a connection between the cost and the time, we can just substitute 8 hours in to our composite function. Okay, so this is going to be essentially c of 10.5 times 8, which is, well, no, I'm going to write it this way. C of x of 8 is now 787.5 times 8 plus 900. I don't know what that is. It's like around 6,000. What is it? 7,200? Even?
Yep.
Oh, there you go. So it costs, that's a lot of money. $7,200 for 8 hours of production. Okay, it either uses a lot of like manpower or expensive equipment or something like that. Okay, and then determine the time that must elapse for the cost to be this. So now we know the cost. We want to know how much time has passed. So we can sub this in for the c of x of t. Okay, and then we can solve for t. So we'll subtract 900 from both sides. And then we will divide by that. I don't know. What is that? How much? 42. No, that sounds right to me. But it's expensive, right? That's the part that's surprising. I know nothing about cars. But producing them is, I guess that's why they cost so much. But if you think about it also, like my car cost new, I think a little more than that, maybe 40 or 38K. So it took, what, like 45 hours to make my car? That doesn't seem like very much time. I don't know. What's that? They must be making a lot of money, those car manufacturers. Okay, that's it for today, and that's actually it for this unit.